continue. Okay, so this is the plan of the talk. The first half of the talk, I'll try to discuss this first 3 or 4 things. So I'll start with physical and mathematical interpretation of the problem. And this part is I'm going to just basically follow the paper of Panulos and Bersey. And then next I will give the explicit hotspot conjecture, what it is, and then some examples, just 2 examples, just to motivate something for later parts of the talk. And then just 1 slide of motivation. And it's not, so you'll see what that is. And then I'll give you the history of the problem, the result that were known before our result, and then our result, and finally I'll focus mainly on this 5th part, our proof of the conjecture for triangle domains. So I'm aware that probably most of you would be knowing almost all of the things that I've discussed in this first 4 parts. So this first 4 topics. So I'll try to be a little bit fast on this part. And if you do have any questions in that part, and I'm being too quick, please don't hesitate to stop me and then ask questions. Okay, so let's start. So starting with the physical interpretation. So the interpretation is the following. So you think of a metal plate, U, and think that this has some initial heat distribution on it, and assume that the boundary of U is insulated. That means heat cannot escape from the boundary of U. Then some heat distribution is on this plate U, and then as T increases, different points on U would have different temperatures. So you look at the points of U where the temperature is highest and lowest. So the hottest and the coldest points of the plate U at a particular time. So these points are called the hotspots of the plate U at time T. So the question that this conjecture concerns is, where are these hotspots located? So again, this is the physical interpretation of this conjecture. So this conjecture says that when T is sufficiently large, all these points lie very close to the boundary of U. Okay, so going towards the mathematical interpretation. So you think of this U as an open connected subset of R2 with Lipschitz boundary, piecewise smooth boundary. Lipschitz is also okay, but let's just take that. And then a heat distribution is a function from R plus cross U to R that satisfies this kind of an equation. So the time derivative is equal to the Laplacian of U with respect to the X variable. And this satisfies some boundary conditions. So at T equals 0, when you start the process, then you have some nice function U0 that is given by the initial heat distribution. And since you have insulated boundary, you have this Neumann boundary condition, namely, so the normal derivative of this function U at every point on the boundary for every time is 0. So, so for T positive, we consider the global maxima and minima of this function ut dot, that's a function from U to R. And these are the hotspots of this function ut comma dot, and this is also by this interpretation, this is also the hotspots of this plate U at time T. So the conjecture says that the global maxima of this function ut dot appears close to the boundary of the domain of U when T is sufficiently large. Okay, so going towards the actual formulation of the conjecture. So under certain conditions on this domain, we can actually express this function as this kind of sum. So utx is equal to C0 plus C1 times P2x times exponential of minus mu times T plus this remainder term Rtx, where C0 and C1 are some constants. And so this mu2 is the second Neumann eigenvalue. Since this is like a geometry seminar, I'm confident that everybody knows what this is. but I'm going to define that quickly in the next slide. And this P2 is the second Neumann eigenfunction. So there is a reason why I have said that under certain conditions, and I have written here that P2 is the second Neumann eigenfunction. So one particular condition that ensures this kind of expression is that when the second Neumann eigenspace is just one dimensional. So on the last part, this remainder term. So this remainder term is has a property that it decreases to 0 at a rate faster than this exponential part. So if you believe that such an expression is true, then recall that we wanted to understand. So the Hawkins conjecture is about the global extrema of this function utx, or it's t as a function of x. Then if you look at this right-hand expression, then you realize that those points where utx attains its global extremas, maximum and minimum, they are completely determined by this function phi2. That's because as t, if you take it t extremely large, then this remainder term do not really contribute much because it's going to be very, very small compared to even this term. And C0 is just constant, so it is going to be there always for every value of x. So it's basically this particular function that will determine where the global extremum of this function is located. I mean, not really, they don't have the same global extrema, but there be, so global extremas of this thing would be lying close to the global extremas of this one. So so once we have this kind of an interpretation or this expression, so we can conclude that basically the conjecture says that the global extremas of the second Neumann eigenfunction in this particular case, this phi2, cannot lie in the interior of the domain. Because if it does, then for every value sufficiently large, all the global extremas of this function would lie close to that particular point. So that would imply that they cannot lie very close to the boundary of all. Okay, so this is I'm going to just quickly give you the definition of the second Neumann eigenfunction. So again, I'm confident that everybody knows what this is. So you take a nice domain with Lipschitz boundary omega, and then you look at the smallest positive number mu to omega, such that there exists a nice function that satisfies this kind of an eigenfunction equation, and also satisfies this Neumann boundary condition. So this smallest number is called the second Neumann eigenvalue, and any function that satisfies this kind of equation and this kind of boundary condition is called a second Neumann eigenfunction. So just to emphasize the fact that unlike the Dirichlet case, where, well, in this particular case also this is the second, so in this case also the first one is simple. So unlike the first Dirichlet eigenfunction, the second Neumann eigenfunction of any domain, so the space of second Neumann eigenfunctions need not be one dimensional. So there could be, the space could be multidimensional. Okay, so one particular other thing that I would like to just mention is that this elliptic regularity implies that this function u is in fact real analytic everywhere in the interior of this domain omega. So that's basically because the Laplacian that we're considering has constant coefficient. Okay, so that's that. Now I'm going to give you the conjecture. So the conjecture basically says that, again, it's attributed to Freud, says that the second Neumann any second Neumann eigenfunction u of any domain attains its global extrema at an cannot attain its global extrema at an interior point of omega. So this can be so in literature there are weaker versions of this conjecture known. So this can be, we can by stating that second Neumann eigenfunction of u attains its global extrema at a boundary, or even further by saying that some second Neumann eigenfunction of omega attains its global extrema at a boundary point. Because again, the second one is coming from the fact that the dimension of the second Neumann eigenspace need not be one dimensional. So this example, so this is, I'm just giving you the examples. So the first one is about this unit interval, and this is, so it's very easy to compute what the second Neumann eigenfunction should be. So it should be the constant multiple of cosine pi times t. And for the square 0, 1 cross 0, 1, second Neumann eigenfunction space is two-dimensional, and it is spanned by cosine pi x and cosine pi y. Now, I'm going to, the reason that I gave just this example is because there would be some reference to this too in the later parts of the talk. I just wanted to mention these two for that part. So now I'm going to give you some motivation. So at least that's what I'm calling it. So basic motivation in this kind of conjectures is probably that the function minimizing a geometric minimization problem should have the simplest possible form. Now, this is actually the case for Dirichlet eigenfunctions. Namely, the first Dirichlet eigenfunction is unique up to constant multiple for any domain with nice boundary. And the result of Braskamp and Leibs says that if the domain under consideration is a smooth boundary and is convex, then the super level sets of the ground state are actually convex. So that's very nice, and this is probably this kind of results probably was the reason why Jeffrey thought about this kind of conjecture. Now, for this particular Dirichlet case, the basic intuition probably is that so if you have a nice convex domain and you're looking at the first Dirichlet eigenfunction, then Dirichlet eigenfunction satisfies the boundary condition that the function vanishes at the boundary. So the zero level set is actually the boundary of the domain, so that is convex. And then probably one can think that a function that does have super level sets convex should have small Dirichlet energy compared to other functions. So that is probably one reason why you should think about this kind of things to be true. Now, if you go to Neumann eigenfunction, it is difficult to say something similar for second Neumann eigenfunctions, and the reason is that so unlike the Dirichlet case, the boundary condition, the Neumann boundary condition implies that the level sets, if you look at of any Neumann function actually, so if the level set is the point where the level set hits the boundary, if that point is not a critical point, it actually should be orthogonal to the boundary. That's what the Neumann condition says. So it's very hard to say what the motivation behind making this conjecture was. So I did send an email to Jeffrey Rout, asking him why he thought that such a conjecture could be true, and he kind of said, if I understood his email correctly, what he thought is that probably if the global maxima lies in the interior, then there might be some way of showing that if one pushes that global extrema near the boundary, then the eigenvalue or the Rayleigh quotient decreases. Anyhow, so let's move on. So I'm going to now give you some results that are known in this conjecture. I'm probably missing a few that came recently, but this is mostly the historical part. So the first positive result is due to Kao from 1995, who proved that a weaker version of the conjecture for domains of the form D1 cross interval 0, 1. So D1 is again kind of nice connected domain with Lipschitz boundary, and 0 is in a nice interval. So if you take this kind of a domain, then the conjecture is true in the sense that the second Neumann eigenspace has at least one eigenfunction whose global extrema appears on the boundary. Now later in this is 1999, Christoph Birdsey and Wendell Werner showed that there is a domain in the plane with two holes that does not satisfy the conjecture. So this is a negative result, and that kind of forced people to believe that there should be some restrictions. So this is the first negative result, and then after that, Birdsey extended this construction even further. So he was able to make it so he later another paper he gave an example of a domain with one hole that also does not satisfy the conjecture. So in all these constructions, he showed that the second Neumann eigenspace actually is simple. So the eigenspace is one-dimensional, and any second Neumann eigenfunction attains its global extrema at an interior point. Now, subsequently, in 1999, Bernoulli and Birdsey proved the conjecture for obtuse triangles, and also, so this is obtuse triangle probably the main focus of the paper, but they actually proved the conjecture for sufficiently flat domains, and obtuse triangle also. So obtuse triangles are special cases of those domains. And in 2000, Jerison and Nadirashvili proved the conjecture for planar convex domains with two axes of symmetry. And a year later, Attar and Birdsey proved it for Lip domains. So just give you what, so Lip domains are domains on the plane. They need not be convex. So they're domains with boundary that can be decomposed into two parts. And so basically, these domains are bounded by the graphs of two functions with Lipschitz constant less than or equal to 1. So they're able to prove this conjecture for this kind of domains. Now, more recent results in 2009 and then in 2013, Miyamoto proved the conjecture for isosceles and right triangles, and in 2015, Bartolomé proved the conjecture for triangles with at least one angle less than pi/6. Recently, we were able to prove this conjecture for all triangles. Okay, so let me just recall. So from now on, so the results that I will explain today are mainly on triangles. Some of the results are actually true for some general domains, but I'll not talk about those. So for the rest of the talk, all the domains that I will talk about are going to be triangles. And let me just recall what were known. So by the result of Bernoulli and Birdsey, obtuse triangles were known to satisfy the conjecture, and by the result of Miyamoto, the conjecture was also true for isosceles and right triangles. And I just forgot to mention that in 2012, the Hospos conjecture was a polymath project under Terence Tau's guidance that was active for about a year and a half. And Bartolomé was actually an active contributor to that particular polymath project. And again, Sudea's result, it is known that any triangle that has at least one angle less than pi/6, the conjecture is true. So let me give you an idea of this parameter space of Euclidean triangles. This would be, I'm going to use something about that. So if you take a triangle in the plane, then up to equivalence, so that's basically homothety and isometries of the R2, up to those things, triangle is determined by the three angles it has, so say alpha, beta, and gamma. And since we are in the Euclidean plane, this alpha, beta, gamma satisfies the relationship alpha plus beta plus gamma is equal to pi. So basically, so if you take this alpha, beta, and gamma as three variables, then the parameter space should be the simplex determined by alpha plus beta plus gamma equal to pi, and that's exactly what this picture is representing. So there is underlying, of course, there is this three axis that is not drawn here. So these things, the points, the vertices are marked according to their coordinates in R3. Okay, so this part that is light bluish part that are marked by this O symbol. They correspond to obtuse triangles, and the part in the interior part, this is a smaller triangle that is light green color, or maybe a little bit gray color. That part corresponds to flat curved triangles. Okay, so basically what's something that it's very easy to see that this thing is actually two-dimensional. So if I take any 2 points on this particular parameter space, I would be able to connect those points by a nice continuous family of triangles the plane. Okay, so let me just yeah. So I'm going to just give you an idea of what were the results known before we even started working on this problem. So obtuse triangles, so this O part were known to satisfy the conjecture to the work of Mondal and Birdsie. And these straight lines, all the straight lines actually. So this, for example, these straight lines, they correspond to isosceles triangle. So this one corresponds to isosceles triangle, and these straight lines correspond to right triangles. So these two triangles, so triangles on these things were known to satisfy the conjecture to work up Miyamoto. And this little bit dark grayish part in the acute part, this corresponds to triangles with at least one angle, acute triangles with at least one angle less than 5 or 6. So this part, triangles in these two parts are known to satisfy the conjecture due to the work of Sugata. Okay, so now before going to our result or jumping into our proof, I'm going to give you a general idea that actually appears almost all the results in particular problem. So here is the idea. So just if you take any C1 function on a domain, and if C be a critical point of the function, then if you take any vector field X and look at the new function X applied on this function F, then this new function xf vanishes at the point C. Now, if furthermore, you take this, so we're going to work with second order eigenfunctions, but if you just take f to be an eigenfunction of the Laplacian and this x to be a very special kind of vector field, it's a killing field. So basically, these are vector fields. So yeah, one way of seeing this thing is that these are vector fields that commutes with the Laplacian. Then if you take such a vector field, then this new function xf is again eigenfunction of the Laplacian. So when I say eigenfunction of the Laplacian, all I'm trying to say is that they satisfy the same eigenequation. So no boundary condition is mentioned here. So in that sense, without the boundary condition, these are, so as soon as I have an eigenfunction and as soon as I have a killing field, I have another eigenfunction xf. So the next important thing that almost appears in this literature is that this very nice result of Cheng that says that if you do have a eigenfunction, so if you take eigenfunction of the Laplacian and then you look at the zero level set, so this Z corresponds to the nodal set, the zero set, the set where this eigenfunction vanishes. So if you take an eigenfunction and you look at the set where the function is vanishing, that function, that particular subset of your domain is actually a very nice subset. Namely, it's a locally finite graph without any isolated vertex or degree of vertex. Actually, what Cheng gives is much stronger than this, but this should be sufficient for me to talk for this particular talk at least. Okay, so once you have this nice graph structure of the zero set, what in this literature people did is that Mondal and Birdsie and the related result of Tata and Birdsie, among all other techniques, what they tried to understand is that what this zero set looks like. So using probabilistic ideas, and when so X is a very special kind of filling field when they're just constant vector fields. So constant vector field meaning vector fields whose integral curves are basically straight lines, parallel straight lines. And then in the work of Miyamoto and Sugata also, they try to understand this kind of nodal set, but they don't use probabilistic techniques. They use analytic techniques, and among other things, Sugata uses test function techniques as well. And in the work of Jason Nadirashvili, they heavily used to study about this nodal sets. So the very novel idea in their work is that they try to understand how this nodal set, again, they were working out with only with constant vector fields and a second eigenfunction of a special type. And they try to understand how this nodal set changes when the underlying domain changes. Okay, so that's That's the basic ideas that were used many times in the literature. So now let me start giving you ideas, some sketch of the proof of our proof of the conjecture for triangles. So our proof has one similarity with this Jerison and Nadirashvili, namely that we also try to understand how things vary when the underlying domain varies. But at the beginning, we do ask a little bit question that is a little bit different than what Jason and others really did. So this is the question that we ask. So we try to ask, what does the critical set of a second Neumann function look like? Does it have to be discrete? Well, this is not necessarily always true that the critical set of an eigenfunction is discrete, and this can be seen easily from the second example that I gave. So if you recall, for the square, the second Neumann eigenspace is spanned by cosine pi x and cosine pi y. And hence, if you take any of the cosine, for example, if you take cosine pi x, then the set of critical points of cosine pi x would include the site x equals 0, for example, right? So it is not in general true that the critical set is always discrete. However, it turns out that it is discrete for triangles. So if you do take a triangle P and a second Neumann function of the triangle, then the critical points of U is finite. Now, once you have this kind of result, what you can do is that you can now try to track the critical points. So I will explain what this means just in a bit. But before that, I would like to give you an idea of the proof of this theorem. So how to see that the critical set is actually finite. So for that, I would like to open this whiteboard. So here is the proof. So maybe I should just go back to here first, then come back here. Okay, so the first ingredient on the proof is this very nice inequality of Polya that says that this is the second eigenfunction of the domain, and this lambda1 is the first Dirichlet eigenvalue of the domain. So the Polya's inequality says that second Neumann eigenvalue is always strictly less than the first Dirichlet eigenvalue for any domain in the plane.
Sugata, sorry, did you share your new screen?
I didn't.
We still see the Fleischmuller space for triangles now.
Wait a minute. Let me. I'm trying to share this. Can you see things changing?
No, it is still the parameter space for Euclidean triangles.
I mean, I do see things changing. I think there's a problem for you.
Maybe it's just on my computer. I don't know.
Yeah, I see it changing too.
Okay, go ahead. Sorry.
Okay, it's okay. So, do you see the proof of theorem? This slide.
This is what I see indeed.
Okay.
Yes.
Good. Okay, thank you. Okay, so yeah, so the one of the most main ingredient is this Polya's inequality, and then this Polya's inequality gives us this one, and I'll try to explain how this thing follows from Polya's inequality. So it provides the following thing. So if you do take a killing field, then you take, so U is the second Neumann eigenfunction and X is a killing field. Then again, as in the last slide, XU is again an eigenfunction of Laplacian, meaning that it just satisfies the Laplace equation with the same eigenvalue as U. It did not satisfy any boundary condition. What this Polya's inequality implies is that if you now look at the nodal set of this new function XU, then that cannot have any loop in the triangle. Now, let me just give you an idea how to see that. So let me first do. Okay. So let's say I do have a loop. Let's say I do have a loop like this. So this is now the zero. So this is, I take something like, so x and u, and then I look at the zero set of that. And this curve gamma is a part of this nodal set xu. Now, if you do have that, then you have, so this is a plane, and we're working on a plane. So this curve would bound some disk, say, just denote that by d. Then what you will have is that the first Dirichlet eigenvalue of d would be bounded from above by the second Neumann eigenvalue of t. That's because this restriction of xu would satisfy the eigen equation with the mu2 as eigenvalue, right? Once you have that, then you observe that this d is contained in this triangle. So by the domain monotonicity of first Dirichlet eigenvalue, what you get is that this number is at least lambda 1 of t. And there you get a contradiction. So this gives you that lambda 1 of t is bounded from above by the second Neumann eigenvalue of t. But as I had by Pauli's inequality in here, I know that that's never going to be true. Okay, so once so this is the proof of this particular implication. Now let's say I do have some, so I'm going to argue, so to prove this particular theorem, I'm going to argue by contradiction. So let's assume that this Q does have an arc. Now look at this. So this Q is the zero of the gradient, right? So so gradient is gradient is a vector field, but you can also think of this as like a norm of zero of the norm of the gradient vector field, right? So that would be a real analytic function on the plane, on the triangle. And then since this, as I had said, this u is actually a real analytic function, this Q would be the zero of a real analytic function in the interior of the domain. There are some issues at the vertices. There are actually, since the eigenfunction satisfies Neumann boundary condition at the sides of the triangle, there's a reflection symmetry. So if you take the triangle and reflect along a side and then extend the function by the symmetry, then then the function extends analytically to the T union the reflected image along the side. So there is no problem around on the sides. There is some issues around the vertices, but let's forget about that particular part for a moment. So at least in the interior part, this Q is a zero analytic function. And hence, every connected component of Q is either a single point or an analytic arc. Now, with a little bit of more effort, what you can see is that if Q does have an arc in the interior of T, then the endpoints of that arc has to lie on the boundary of T. Now, let's assume this part for a moment, and let me just give you a proof of this thing that I prove that there cannot be an arc, so that's what I'm to prove. So let's argue by contradiction. So let's say I do have an arc. So by this, by the previous argument, you can already see that there cannot be a loop, right? That part is okay. Now let's say it does have a that's not clear. So let's let's take there's an arc, and if that arc is forms a loop, then the argument would actually, this argument that I'm going to give you would also imply or would actually work for if this arc were a circle. Okay, so let's this red arc, this red arc gamma be a subset of the crit of u. Then what I'm going to do is that, so since this whole gamma is a subset of crit of u, then if you take any Killing field x, then the zero set of xu would actually contain this curve gamma, right? That's it just follows from the definition of critical set again. Okay, so that's good. And now I'm going to choose a very nice vector field in a very special way. So this arc gamma intersects the boundary at 2 points. So I'm taking a very simple curve. So let's say let's take this vertex, this particular vertex, such that the two ends of gamma lies on the two sides that are adjacent to this vertex V2. Okay. Now, what I'm going to do is that I'm going to consider a very special vector field corresponds to this V2, and that's the rotational vector field. That's going to be this kind of vector field called a rotational vector field. So what is this? So if you want to take a point A on the plane, then there's a vector. So take the vector field given by this kind of a formula. This is a vector field whose integral curves are actually circles with center at that point A, and yeah, it's the same direction, of course. So if you take this kind of vector field, then what would happen is that since my eigenfunction U satisfies the Neumann boundary condition, what would follow is that these two sides. So I'm going to take this R. So I'm going to apply. So now so X is equal to R of V2. Then if you take that X, then this arc was already in the nodal set. And then when you apply this, because the function U satisfies Neumann boundary condition along the sides, it would imply that the nodal set of this function, so nodal set of Z of R V2 of U would contain these two sides, this side and that side, right? So once you have this side and that side, and then you already have this curve, then you see that you have a loop, right? Yeah. So that's the proof. Okay, so that is basically what I have tried to say here. So gamma is the arc in there, and then you look at the vertex where the endpoints of this curve gamma lies, and then you take a rotational vector field nicely, and then you get a contradiction to this first, the second point in this slide. So we find that XU has a loop in Z of XU has a loop in the triangle. Okay, so now I'm going to go back to what I meant in this last particular thing. So once I have this result, I know now that the critical points are actually finite. And then what I can do is that I can try to track those. What do I mean by tracking? So this is what I mean by tracking. So I start with a very explicit triangle, namely it's the right isosceles triangle with these explicit vertices. So I take the 0, 0, 1, 0, and 0, 1 as these three vertices. And then, so this triangle, for this particular triangle, the second Neumann eigenvalue is known, and its eigenfunction is also known. It is known that the second Neumann eigenspace is actually simple, one-dimensional, and any second Neumann eigenfunction is a multiple of cosine pi x minus cosine pi pi. So once you have this expression, you can by hand compute and see what its level sets are, and then you can also compute where the critical points of this function lie, and then you realize that this function has no critical points at any of the points, so not on the sides, not in the interior, no critical points at all, except the vertices. Okay, so once I have that, then again I'm going to argue by, so the argument is by arguing by contradiction. So let's assume that there is a triangle T naught such that a second Neumann eigenfunction U naught of T naught has an interior critical point. Now the next thing what we do is that we join. So again, I'm going back to the parameter space of the Euclidean triangles. That's a simplex. So I can connect T naught and T1 by a nice path of Euclidean triangles in that parameter space. And this next part is not necessary, but it's very easy to. That assumption is very nice to have in mind because it makes life a little bit simpler. So I assume that the second Neumann eigenspace of all these triangles is actually one-dimensional. So this is a very nice, this is actually true. So it's the second Neumann eigenvalue of any triangle except the equilateral is actually simple. Multiplicity is actually 1. And this is known due to works of many people. For example, for obtuse triangles, this is a result of Formulation and Berzy. And for isosceles and right triangles, this is due to Miyamoto. And for other acute triangles, this is a result due to Sugata. Now, once you have this kind of result, what you can do is that you can use perturbation theory a little bit. And what you can do is that corresponding to this path TT of Euclidean triangles, you can actually find a nice continuous family UT of functions such that UT is second Neumann eigenfunction of TT. Now, when I say this, one has to just be a little bit careful. So what one has to do is that one has to fix a model domain, model triangle, and then think of all this other Euclidean triangles as some different Euclidean matrix on this particular domain or model triangle. And by saying this UT, this UT is a nice one-parameter family of second Neumann functions, is that so this UTs are going to be functions for each T. UT is going to be a function on this model space, and U2 is going to be satisfying the second Neumann eigenfunction equation for Tth Euclidean metric on the model space. Okay, so once I have that, the question that we ask is that by assumption T0 has some critical point in the interior of the triangle T0. Then where did this critical point go as T moves from 0 to 1? Because as I also have mentioned that as we move to U T equals 1, the second Neumann eigenfunction of this thing is going to be a multiple of this nice function that has no critical points at all. So somehow this critical point of U0 has to go away as we move along T. Now this question is actually a bit naive, because many things can happen. So, namely, the initial critical point of U0 may be actually degenerate. So, if it is degenerate, it can just go away immediately and it might not appear for any T at all. Now, even if you assume a stronger assumption that the initial critical point is actually non-degenerate, it can happen that as T progresses, the critical point become degenerate and then go away. It can also happen that the critical point can go to a vertex, or theoretically can go to a vertex or a site. Now, the first major step in our approach is this result that that is in some sense shifting of focus from the interior, so which the conjecture says. The conjecture says that there is no global extrema cannot be in the interior. So basically, the conjecture is about things that happens in the interior, but then shift the focus from the interior to the boundary of the domain. So what this theorem says is that so if you take a triangle T and give a second Neumann eigenvalue of T, then if you do have an interior critical point of view, then you already has 3 critical points. I'll just explain this part a little bit more. So of non-zero index on boundary T, and in fact, I should emphasize this more. So each side of T has a critical point of view in it. So I want to give an idea of the proof of this result as well. But before that, so I want to just emphasize something about this possibility that I mentioned. So basically what I'm trying to say is that the stability of the critical point is important to even try to track, right? So I do know that they're discrete, but I don't know whether they're stable or not. So they may be stable at the beginning, but there is no guarantee that they don't become unstable in between, and I might not be able to track that. So that's the issue here. So I want to give you an idea of what can happen. So it's not very difficult to imagine, but probably explicit example or pictorial example is helpful. So this is a picture that can happen. So at the beginning, so for some T, probably the picture looks like this. So you have a local extrema in here and a saddle critical point over here where 2 level sets are crossing. And as time progresses, these 2 critical points come close and they collide at this particular point here. and somehow they become the index 0 critical points. So I'll explain what that is again just in a minute. And then after that, once this becomes something like this, and then it just resolves itself, and there's no trace of the critical point anymore. So this kind of thing can happen, and in fact, this kind of thing does happen. So you can, if you just allow a little bit more general situation, it is possible to construct an example where this thing does happen. So this is not, it is pointless to try to prove that that thing never happens. So it is actually possible. So that's actually what is the issue here. Now I'm to give you an idea of the proof of this particular result. We have some time. Before doing that, again, I would like to just give you an idea. So here I have said that the index of the critical points are non-zero, the new critical points that I can find once I have something in the interior of the triangle. So the index by definition is that, so what you do is that you take a critical point and of a function u, and then you look at the gradient vector field of u. So this, if you take a critical point, then that point is a 0 of the gradient vector field. Then what you do is that you basically try to find the index of that 0, and that's by definition is you just take a small circle around the critical point, and then you take the self map of circle to itself by sending a point on the circle to grad x by the norm of the grad x. So again, this index, the definition depends. I mean, you have to ensure that this is an isolated critical point. So so this is the definition of the index, but in dimension 2, there are easier ways of seeing the index of a critical point. It turns out that if you do have a local extrema like this, so again, since this is function, it's an assumption that I'm considering satisfies the Laplace equation. If you do have a local extrema, then the level sets near there do look like the circles. And then the index critical point, index of this kind of local extrema becomes +1. So this is an example of a critical point where these two arcs are crossing each other, and like in this particular picture, like in this picture over here, this particular one. So where the index is -1, and again, if you now increase the branches, then the index is going to be decreasing. So again, let me just again recall, just repeat myself. So these are level sets of the function. So these branches are basically level sets. So since I am working with eigenfunctions with corresponds to the Euclidean Laplacian, things are all analytic, so I can actually make my life simple about the index by just by looking at this number of arcs that crosses through the critical point. Okay, so this is so it is more or less clear from this kind of pictures that if you do have some critical point that has index non-zero, then they cannot just vanish immediately. It needs some argument, but I hope it is more or less trivial. Okay, so let me just I'm going to give you an idea of the proof of now this particular theorem. So that says that if I do have a critical point in the interior of the domain, then I already have 3 critical points, one in each side of the triangle, and they all have index non-zero. This part I just give you a vague idea, but I'll not be able to give you a complete proof because the complete proof requires some analytic argument. Okay, so for the first part, so let's say I do have a critical point here, somewhere here of my function u. Then what I'm going to do is that I'm going to just do exactly what I did up there. So I'm going to take this vertex, so let's say I want to prove that this side contains a critical point of u. So what I'm going to do is that I'm going to take this vertex v2 here, and then I'm going to take a look at this again, rv2u, and the nodal set of that. So I already know from the last argument that these two sides are in the nodal set, in this particular nodal set, zrv2u. Now I also know, since this particular interior point is a critical point, this point is also in the nodal set of rv2u. Now here comes this result of Cheng. So Cheng's result says that the zeros are zeros. So again, RV2 is a killing field. So RV2U is a eigenfunction of the Laplacian with the same eigenvalue as U2. Again, need not specify boundary condition, but locally it's eigenfunction. So Cheng's result provides that the null set near the particular point cannot look like this point, so there has to be some arc going through that. And actually, it also provides, with a little bit of work, that the endpoints of this arc cannot be in the interior. So it has to hit somewhere on the boundary. Now, by an argument similar to the last argument up there, the endpoints cannot actually be looking like this, because then this nodal set would have a loop in there, right? So then we would at least have, so at least one of these ends of this arc has to end on this side opposite to V2. Now I'm claiming that this particular point where this arc hits the opposite side is a critical point. So let's call that point P, and that I'm claiming that P is a critical point. So P belongs to crit of U. And why is that? That's because if you look at your vector field again, so RV2 is a rotational vector field. And if you look at this vector field at that particular point, it is somewhat like, so you take this thing and it is somewhat going to look like this. So it's not going to be, so basically what matters is that vector field, so RV2 near at the particular point P is not going to be parallel to the normal direction field. So basically the RV2 at P and normal vector field to the side opposite to V2 at P, they're linearly independent. Now since U satisfies normal boundary condition, I already know that the normal direction derivative of U at the point P already vanishes, and then by this argument I already know that, so I also know that the RV2 also vanishes at the point P. Hence, two directional derivatives vanish at the point P. They are linearly independent, and hence P is a critical point. Right. So that's the argument that I do have a boundary critical point opposite to. So I do have a critical point on the side opposite to V2. And similarly, I can argue with other vertices to find a critical point that lies at the side opposite to other vertices. Okay, now finally, so just to give an idea of why this critical point has to be a non-zero index, that is a bit difficult, but let me just tell you this, that if you do have a zero index critical point, then all these nodal sets are going to have, so if you just take if you do take let's say if this is a zero index critical point, and then you take any vector field, any killing field like that, then what is true is that all this, so take some killing field and look at the nodal set passing through that particular critical point C, and if that index of C is 0, then the tangent direction to that particular curve at the particular point, assuming that there is exactly one curve passing through C, is going to make the same, it's going to be parallel always, independent of the killing field that you take. And that actually implies that if you do have a zero index critical point, then this arc that is reaching here, it cannot actually cross like that. It has to be coming like that somehow. Again, this is a vague idea. This is not a proof. But anyhow, so this is basically the idea that particular critical point cannot be a zero index one. Okay, so that's the idea of this particular theorem. Now this is good in the sense that so we now have more critical points and they're on the boundary, so maybe they're helpful. But if you look at the first two conditions here that I mentioned, the possibilities that can happen, you realize that the boundary critical points can also be degenerate. They can also become degenerate if they're not degenerate at the beginning, and then they can try to go away. Now, a very interesting thing that kind of made us hopeful that this approach might work, is this nice result that says that that if you might have a degenerate critical point at some particular point time t, but what would happen is that if you do have something like that, then there's another side of the triangle that does have some critical point that is not going to be unstable. So that to be more precise, so if you take a triangle T and a second normal function U, and if C be a degenerate critical point of U that lie on the side of T, then you have another critical point P of non-zero index on another side that is different from T. Okay. I wanted to give you an idea of the proof of this one, but I don't have any time. So I'll not go to that. So now to address this third point here, what can happen around the vertices. So in a way, actually, the critical points can go to vertex, and actually we do know that situation when a critical point does go to a vertex. But what happens is that there are nice consequences in the sense that something happens to the eigenfunction when a critical point does converge to a vertex. And what we do is that we develop a theory along these lines, and we were lucky to be able to find a proof of this conjecture for all triangles. Now, I would like to, before concluding the talk, I would like to mention a little bit a few points. So the point is that if you have already taken a look at the published version of our work, then you realize that the statement of this theorem that I've given here is stronger than the one that appears in the published version. Namely, this non-zero index part, this thing is something extra. So I would like to announce here is that the proof that is published here for acute triangles is actually that has a gap. It's not completely correct. So this is why I have in this talk I have included this particular stronger assumption, and yeah, so we found the gap couple of like 5-6 months ago, and then we were lucky to be able to find a fix for that, and hopefully we will be able to update publish that fix soon enough. And yeah, that's where I stop. Thanks for listening.
Thank you very much for this very nice talk. I'm sorry about the problem. I had a problem with my Zoom and it stopped completely. So I think someone else became host for a while, but now I'm back. Hopefully you can hear me. And we have time for questions. So please, if you have questions, you can ask them or write them in the chat.
I'd like to ask a question, if I may.
Yes.
So thanks for the nice talk first. I would like to ask, of course, the kind of obvious thing, how much of this can be extended to more general convex, for instance, convex polygons, and where are the challenges to do that?
Yeah, so we have been able to, so I think I mentioned this, so this result of, yeah, that's a very interesting question, and this is something that we have been working on that for some time now. Yeah, so this result of Tata and Berzi, they did look at more general domains. So these are basically, in a way at least, domains that are obtained from obtuse triangles. And the Lib domains that I'm talking about, so they are domains with boundary that are graphs of two functions with Lipschitz constant less than or equal to 1. And they proved the conjecture for those kind of domains. And what we found is that actually our method actually gives a new proof for this particular type of domains. And our result might be a little bit stronger, but maybe just the same. We have to just look at that to what extra we can say. So yes, it can be extended to that. So that I have already been able to do. But for other domains, like if you look at domains that can be obtained from acute triangles, for example, right? But those domains, yeah, we're still trying, and we still don't have any idea of how to extending this. Mainly, so let me just give you why the main issue with acute and obtuse. The issue is that, in the case of obtuse triangles and the domains, the slip domains, the point is that the second Neumann eigenfunction is expected to have no critical points at all. So that's something very important. That's something important in the sense that, so if you look at the last lemma that I gave you, so that says that if you do have a degenerate critical point of a triangle, then you already have another one, which is not unstable in some sense. Now, this result is sufficient. So all the results that I've given so far in the talk, that's sufficient to prove the obtuse case. But it's not sufficient for acute, because for the acute case, you actually expect to, an acute triangle is likely to have extra critical point. It's likely to have one saddle critical point. And that's the problem. So these lemmas cannot give you more than one. So if you have to argue along these lines, then you'd have to somehow create more critical points to get a contradiction. But so far, these arguments are not strong enough to, for general domains, it's not strong enough to provide any extra critical points in a sense. So that's where the challenge is. Yeah, so if you can find other ways of showing that some bad critical point implies existence of some more nice critical points, then yeah, this approach might work.
Thank you.
Thank you again very much, Sugata, for the very nice talk.
Thank you for this.
Thank you everyone for being here.